Welcome to lecture 16. In this lecture, I will talk about the covariant derivative. Recall that in lecture 10, we derived the geodesic equation. That's a second-order differential equation that embodies the trajectory that a particle has to take in order to have minimum time to go from one point on the manifold to a second point in the manifold. We discussed that this equation, or one meaning of this equation, is that the second derivative of the coordinate x mu with respect to proper time tau is not a vector under coordinate transformations. Essentially, this term is the reason. This basically spoils the general covariance of the second derivative here. So the point of introducing a covariant derivative is that we will use it as a new operation that repairs the property of a concept of not being a vector under general coordinate transformation. So we want to have an operation that generates vectors and other tensors under general coordinate transformations. So that's the point of the present lecture. Okay, in order to get started, recall that we are interested in nonlinear coordinate transformations, those where the coordinate change dx mu to dx prime mu is expressed by this transformation matrix R mu nu, which itself can or will depend on the coordinates. In the geodesic equation, we have the Christoffel symbols gamma, mu, alpha, beta, and we can ask ourselves how these actually transform under these coordinate transformations. It is possible to calculate that. We can either use the specific expression of the Christoffels in terms of derivative of the metric tensor, or we can go back to lecture 10 where we had an expression of gamma, mu, alpha, beta in terms of derivatives of coordinates. However you proceeded, the exercise is a little bit tedious, but not too much. And you can find that this is the transformation law of the Christoffels from the unprimed coordinate system to the prime coordinate system. So essentially what we have is we have one piece here, which involves three of the transformation matrices R, one acting on each index of the original symbol. So if you had only this piece here, gamma, mu, alpha, beta would be a tensor under coordinate transformations. However, we have a second piece here, this one, that involves the derivatives of coordinates with respect to, so the prime coordinates with respect to the unprime coordinates and other pieces here. So because of the second piece here, we find that gamma does not transform under tensor under general coordinate transformations. This is not surprising. Basically, it will happen generically when we have some quantity such as a mu being a vector under coordinate transformations. The derivative of that vector will in general not be a vector or tensor under coordinate transformations. And the reason simply is that if we have a mu transforming to a prime mu given by the transformation matrix dotted into A, the derivative will pick up a contribution that acts on these coordinate-dependent transformation matrix. So in detail, we have d nu a mu going over to d prime nu a prime mu. That is the same as d prime nu on the transformed vector a prime, and that transformed vector a prime is just given by transformation matrix times the original vector. So using the chain rule, we get two terms. One of them is the transformation matrix acting on the derivative of A, and the second piece where we have A and the derivative acting on the transformation matrix. You can see already here in the equation 16.4 that if we only had this first term here, the transformed derivative would also have a transformation matrix that would basically say that this piece here is what we expect of a rank 2 tensor under general coordinate transformation. But the second piece here, where the derivative acts on the coordinate dependence of the transformation matrix, that piece here spoils general covariance of this combination here. So the derivative d nu of any vector a mu is in general not a tensor under general coordinate transformations. We can be even more explicit. We can write down the expression, the specific expression for the transformation matrix R mu alpha. So recall this is just the derivative of the new coordinates with respect to the old coordinates. And then in the second piece where we had the derivative of the transformation matrix with respect to d prime nu, we can write this as a derivative with respect to x beta, and then we get dx beta with respect to d x prime nu. So that is the derivative of r mu nu written out very explicitly. Why do I do this? Well, it turns out that if you compare this with the transformation matrix, the transformation of the Christoffel symbols themselves, which we had in this equation 16.3, let me quickly go back here. That sort of looks kind of similar, okay? So there we have a derivative of these coordinates with respect to two alphas. Okay, we have two of these pieces here, but one of them sort of certainly looks like what we have in our transformation here. So it turns out that in particular, if we take out another one of these, so if you multiply this by the inverse transformation matrix R, so that R mu alpha is acting as a multiplier on this thing in parentheses, then it turns out that we can consider the combination d nu a mu plus this Christoffel symbol and look at the transformation matrix, the transformation properties of this thing. We will denote this combination. So where we take the usual derivative of the vector A and add the Christoffel symbol that has the same upper index as the vector we're interested in, one index that corresponds to the derivative, and one new index row that goes together with the vector itself. We will define this thing together as a new symbol, nabla, with an index nu acting on a mu. And we will call this thing the covariant derivative. The point of writing the expression in 16.5 very explicitly is that it is not too hard to verify that this thing here, this offending term that comes from the transformation matrix of the usual derivative on A, actually cancels exactly with respect to the transformation term that we get for the transformation of the Christoffel symbols. So basically, we have that the derivative contains one term that spoils general covariance. The transformation properties of the Christoffels also contain exactly one term that spoils general covariance. And if we look at this particular combination, we can make it such that these two terms actually cancel with respect to each other, and we only get terms that respect general covariance. So in this particular case, if we look at the coordinate transformation of this object here with the covariant derivative, then it is not hard to show that this object here transforms such that we get the same object back and the corresponding transformation matrices are for the upstairs index and are inverse for the downstairs index. So that is indeed what we expect for a quantity that transforms according to general covariance. And it is basically by construction because we have canceled the offending pieces that spoil covariance by adding this Christoffel symbol here. Okay, so that was one example for repairing general covariance for the derivative of a vector. It turns out we can generalize this idea to arbitrary rank tensors. So if we have an arbitrary rank tensor, we call it X. It has n upstairs indices and m downstairs indices. And we want to take the derivative with respect to nu, the covariant derivative with respect to nu of that thing here. Then we define the covariant derivative of this arbitrary rank tensor through the following definition. We'll have a usual derivative with the same index acting on the tensor. And then for each upstairs index, we add a Christoffel symbol that has this index. We replace this particular index by a new index alpha. So this is the first index, mu1. We have to add a second one for mu2. And then we sort of go on all the way to the last index, mun. And then for the downstairs indices, we do it in a similar fashion. The only difference is that we add a minus sign for the downstairs index. So we have a minus gamma beta. So the upstairs index now is the one that's contracted with the position of the downstairs index in the rank in the arbitrary rank tensor that we replace. And one of the downstairs indices carries the particular index that we are replacing. So this is the first one, second one, and so on until the last one that we had to replace here. So that is our definition of the covariant derivative for a rank n tensor. And the claim is that these combinations that are generated from this covariant derivative defined in this fashion transform properly as tensors under general coordinates transformations. As I said before, we will call this symbol nabla with an index the geometric covariant derivative, and we will employ this symbol in order to distinguish it from the usual derivative, the usual 4 gradient that I'll write as partial mu. Why did I sort of call this the geometric covariant derivative? Well, it turns out that there is a notion of a covariant derivative also in gauge theories, where the appropriate connection sort of is provided by the gauge field. Here in gravity, just to make sure that this is the proper sort of thing that we sort of want to make covariant is the point is that we are interested in geometric properties. So gravity has something to do with geometry. So that's why, to be very specific, this is called the geometric covariant derivative. Also, for instance, if you're interested in looking at a theory that combines gravity with, for instance, electromagnetism, you have 2 covariant derivatives, the geometric covariant derivative, this one here, and the gauge covariant derivative. Anyways, so this is just a side note. For us, we will basically just deal with gravity proper. So we will always mean the geometric covariant derivative when I say covariant derivative. Okay, what are examples for the covariant derivative? So for instance, we can consider the covariant derivative acting on a scalar x, so something that has no index at all. In this case, because there are no indices, the covariant derivative is just equal to the normal derivative acting on that same scalar. For vectors, this is the property that we had in our example before. The covariant derivative acting on the vector x mu is defined as the usual derivative on the vector x mu plus the Christoffel symbol that carries the same upstairs index as the vector, carries the same, one of the downstairs indices is the same as the derivative we're interested in. And then the second index that is downstairs is the one that's contracted with the original vector that we have. And if we had the index mu downstairs, we would have a similar construction, but we would have a minus sign over with the Christoffel symbol. For rank 2 tensors, then, we have the same idea. So the covariant derivative acting on the rank 2 tensor is equal to the usual derivative acting on that tensor plus the Christoffel symbol with one of the upstairs indices matching the tensor we're interested in, and somehow I switched notation from x to t. I apologize. These should both be x's. And there's a second Christoffel symbol that carries the second upstairs index here. And again, this should be x instead of t. So what is the meaning of these covariant derivatives? It turns out that covariant derivatives generalize certain flat space identities, so identities that we are accustomed to having when we are dealing with sort of Minkowski space, basically. So for instance, we have talked quite a bit about conservation laws. So for instance, the conservation of the 4-vector JMU equal to 0, that's a consequence of the Noether theorem coming from essentially the conservation of or the symmetry of gauge invariance. And this is an identity that is in Minkowski space expressed using the usual derivative. However, it is, as it clear from the previous discussion, this here is not a statement that's covariant under general coordinate transformations, so those that are expressed in equation 16.2. So instead, the correct conservation law for a space that is curved would be one that has the covariant derivative acting on this same vector here, not the usual derivative. This has important consequences. We can split this in terms of the usual derivative and the Christoffel symbol, and I can bring the Christoffel symbol to the right-hand side. So what that means is that on a curved manifold, we'll have that the four derivative of the current J mu is equal to minus the Christoffel symbol here with two indices the same, because basically these two indices are the same here, acting on this vector density J mu or J alpha. And what that means is that the four derivative of that vector is actually not equal to 0. Okay, so in some way, basically, it means that the conservation law, so the conservation of the current, is not true if we are thinking about a curved manifold. There is an effect from the geometry, and the effect will be that the conservation law that we are used to having in flat space no longer holds in curved space. This is sort of like a Coriolis force, okay? So basically, it's not a real force because this is just the geometric contribution from the fact that you're not in a flat space-time. But the sort of effect is there anyway. So think about a spinning sort of disk here and walking on this. You'll feel a force that sort of will try to sort of drive you away from the center. And that force is not real because it's just a coordinate change from a stationary coordinate system to something that's rotating. But nevertheless, you will have a real effect, which is that you're being driven away from the center through the fact that the disk is rotating. So it's not a real force, it's a fictitious force, but you'll feel it anyway. And that's basically this idea here. So this violation of the current conservation law is not due to some sort of real effect, if you want to, the way that we usually define real forces, but it is something that will sort of change. So basically your charge will no longer obey d mu, j mu is 0, but it will obey this particular conservation law here. Note that this is also the reason that sometimes people will say that gravity is not a real force. We'll find that the whole effect of gravity, which we still have to formulate in the theory of general relativity, is due to this fictitious geometric sort of effects here. And that's one particular way that you can think about it. But in practice, it doesn't matter because the effect on sort of objects will be there and will be given by these sort of geometric sort of forces. And whether you call this a real force or fictitious force doesn't matter because the end effect is the same. Note that this fact that we have to replace flat space conservation laws by curved space variants is true for other conservation laws as well. So for instance, for the energy momentum tensor, we have derived this before, and in flat space, this was just given by the law that d mu t mu is equal to 0. So now in the proper generalization of this to curved manifolds is the one that has a covariant derivative acting on the tensor instead of a usual derivative. So again, if we split this out in components, we have the usual derivative plus two terms that involve the Christoffel symbols acting on or contracting with the energy momentum tensor. And that you can sort of clearly see that since we have this piece here plus some additional pieces equal to 0, this means that the usual derivative d mu t mu is no longer equal to 0. We can bring this on the other side and sort of make it explicit. And essentially what this means is that in curved spacetimes, energy conservation is kind of tricky, okay? So there is no trivial sort of notion of conserved energies anymore that we're used to in Minkowski space because we can have curved manifolds and there are additional terms that sort of arise that come from the fact that the sort of space-time may be curved. In static situations, so static spacetimes that sort of, where the manifold is sort of curved but doesn't change, you can still sort of make sense out of energy through basically the same conservation law here, but it becomes very tricky once you are in a dynamical situation where basically the space-time changes as a function of time, because then defining energy can become very tricky. Simply put, it will be impossible to define energy and energy conservation in general sort of dynamical situations such as cosmology and stuff like that. We can define it when basically the change is not too rapid. So we can sort of say, okay, it's almost static, and we can sort of make a notion of energy that sort of obeys some sort of consistency checks. But when it's highly dynamical, energy conservation basically disappears, and we will have to think very hard what we mean by this. Nevertheless, we still get sort of laws such as the geometric covariant derivative on the energy momentum tensor equal to 0 that always hold. Okay, so these things are still there. They're just not very easy to interpret in terms of the usual conservation of energy and momentum when we talk about dynamical spacetimes. And this concludes the present lecture.